Alrighty guys, let's go ahead and take a look at some of these problems here. So this is Newton's second law, homework number 1. It says for each problem on this side, we want to draw the free body diagram and set our coordinate system. So we always know that our coordinate system is going to look something like this, where this is the positive y direction, this is the negative y direction, this is the positive x, and this is the negative x. Calculate the net force in that x direction. Does the object accelerate? If so, which direction? Calculate the acceleration. All right, so we got a lot of stuff going on. Let's start with the first one. A person pushes a 10 kilogram box to the right with a force of 5 newtons across frictionless ice. So for the free body diagram, I'm going to start by drawing my dot. You can use a box if you want, whatever works. We always know that there's gravity, and gravity is always pointed down. Next, it says that they push this box. Well, if they're pushing the box is on the ground. If the box is on the ground, that means that I have force normal pointed perpendicular from that ground. Lastly, they're pushing it to the right, so that means that I'm going to have a force applied pointed to the right. There's no friction because it says frictionless ice, so no friction. Okay, now that we have our forces identified and our free body diagram drawn, we can go ahead and start calculating our net force. I'm just going to go ahead and label my forces over here. So direction, it says X or Y. I'm going to go and write up and down here. And the force that pointed up, we knew was force normal, and the force that pointed down was force gravity. And then in the X, it's to the right, and the force that points to the right was force applied. Okay, now that I have that taken care of, again, I'm going to solve for the net force calculations. Well, if we look, we know that normal and gravity are equal to each other, and they're equal to each other because this box is moving to the right, it's not moving up or down. Therefore, the net force in the y direction is 0. How do I solve for force gravity and force normal? Well, it doesn't really tell me to do that. It just tells me to solve for the net force. So now we need to solve for the net force in the x direction. And we know that net force is equal to mass times acceleration. But we also know that net force is equal to the forces that point to the right, in this case force applied, minus the forces that point to the left. There's no forces pointing to the left, so that means that our net force is just equal to force applied. In this case, that would just be 5 newtons. I can take that, plug that in here, and plug that in right here. Okay. If I did want to solve for the force gravity, I could do that really quickly. I know that force gravity is just equal to mass times gravity, and I know that the mass is 10. Therefore, it would just be 10 times 9.8. Giving me 98. On this side, we don't need to solve for the force gravity, but on the back side we will. Now it asks us, what is the acceleration value? Is it positive or negative? So I actually know this answer before I even solve for anything. Because if I look at my free body diagram, I see that it has unbalanced forces and that there's a bigger force pointed to the right. And if it's pointed to the right, that means that it's going to be a positive number. It's asking for the specific value, so in order for me to do that, I need to take my equation, which is net force equals ma. In this case, I knew that my net force was 5, so I would write 5 is equal to the mass, which was 10, times acceleration. When I solve, I find out that my acceleration for this problem should be 1/2 meters per second squared. It's asking the direction, left, right, up, down. Again, this one I already know. It's moving to the right because that's where the bigger force is pointing. Let's take a look at number 3. Number 3 says a person pushes a 10 kilogram box again to the right with a force of 5 newtons across mud. The force of friction, so this time friction does matter, pushes to the left with 5 newtons. So if I draw my free body diagram, I'm going to start with gravity pointed down. It's on mud. Mud is a surface, so I'll have normal pointed up. And then I have the force applied, pushing it to the right, because that's what it says. And then I have force friction pushing back at it to the left. Okay. We should be able to draw these arrows very accurately with the size of them, but if you're confused, you can always hold off and erase and draw them correctly at the end. So let's get back to the net force calculations. So in the y direction, the upward force was force normal. In the y direction, the downward force was force gravity. And we know that net force is 0 because it's not accelerating up or down. In the x direction, the rightward force was force applied this time. And the leftward force was force friction. So in order for us to figure out this net force, we're going to take our equation and say that the forces that point to the right, which are force applied, minus the forces that point to the left, which is force friction. So I can go ahead and plug these numbers in. Force applied is 5 newtons, so 5 minus, and then force friction is 5 newtons. 5 minus 5 is just 0. Therefore, our net force in the x direction is 0. So 5 and 5. So now we want to figure out the acceleration value. So again, it's talking about number, positive or negative. So the value of the acceleration, well, we know that net force is equal to ma. If the net force is 0 and the mass is 10, then what is the acceleration? Well, if I solve for acceleration here, I get 0 divided by 10. 0 divided by anything is just 0. Therefore, the acceleration for this problem is just 0 meters per second squared. So when it asks what direction is it accelerating, it's not accelerating. So therefore, it is no direction, or I'm just going to write not accel. All right, let's take a look at some of these y direction problems. So these problems describe a person's trip on an elevator from the ground floor up to the top of the building. The person's weight is 784 newtons. And again, weight just means force gravity, so that's important. The 80-kilogram person gets on the elevator and pushes the button to the top floor. The elevator is not yet moving. So that's also really important because when it's not moving, it means that we're at rest. So if we want to draw our free body diagram, we know that we have force gravity pointed down. And even though they're in an elevator, I know a lot of you guys are thinking, oh, force tension because there's a cable, but it's the person. The cable is not pulling the person, the cable is pulling the elevator. What is actually being applied to the person is the elevator floor, so therefore it is force normal pushing up on that person. So for this one, we know that we have an upward and downward force. In an elevator, there's no x direction forces, so we don't need to worry about that one. The upward force, like we said, is normal. The downward is gravity. It tells us that the weight is 784 newtons, so I can plug that in right here. And it also tells us that we're at rest. So if we're at rest, acceleration is just equal to 0. If acceleration is 0, the net force is 0. So this net force is 0. If that's the case, what does force normal have to be? Well, force normal needs to be the exact same number as force gravity in order for it to be balanced and at rest. So acceleration 0, direction none, because it's not accelerating. That was pretty easy. Let's move on to number 6. So number 6, the elevator door closes and it begins to accelerate upwards. The elevator floor pushes up on the 80-kilogram person with a force of 800 newtons. Okay, so now the floor is pushing up. So we know that we have gravity pointed down and the floor is pushing upward. So the question is, are these arrows the same size? Since we're accelerating upwards, the answer is no. Which one's bigger? Well, it kind of tells us. It says that we're accelerating up. So our arrow is going to be bigger in the direction of acceleration. So the force normal should be bigger now. And we can see in our diagram that force normal is bigger. So net force, we know that net force is equal to the forces that point up, force normal, minus the forces that point down, force gravity. And in this case, the force normal is 800 newtons because it tells us right there. Force gravity, well, we were told force gravity all the way back here in the beginning. Force gravity is just 784. So I'm going to write that over here. And then now I solve for net force. When I solve for that, I find out the net force should be 16 newtons. So I'm going to go over here and fill in my chart. 16, up, down. Again, there's no x direction forces. The force pointed up is the force normal. The force pointed down is gravity. Normal was 800 and gravity was 784. Ugly 4. Acceleration value, we know that net force is equal to ma, and the net force was 16. the mass, well, the mass is just given to us right here. The mass is 80 kilograms. 80, and the acceleration is unknown. Solve for A, divide both sides by 80, and we find out that A should be equal to 0.2 meters per second squared. It asks what direction, but it also tells us that in the problem. It literally says accelerates upwards. So the answer is up. We also know that it's up because this is a positive acceleration, and the positive direction in the y plane is the upward direction. Let's take a look at number 8. So number 8 says the elevator gets close to the top of the building and starts to slow down. We say decelerate, just meaning like negative acceleration. The elevator floor pushes up on the person with only 400 newtons now. So again, I have force gravity pointed down, and this time force normal is not as big because it tells me that it's only 400 newtons. So this right here is my force normal. So I'm going to go ahead and write my forces over here just like I've been doing, where normal points up, gravity points down. So normal is now 400. Gravity is always the same. We know that gravity doesn't change. Now I'm going to go back to the previous page to see what it is. 784. So I'm going to write that right here. We know that the elevators don't accelerate in the x direction, so we can get rid of all this garbage. Now we're going to take our net force equation. Forces that point up, force normal, minus the force that point down, force gravity. Net force is equal to, well, force normal is 400 and force gravity is 784. When we do the math, we find out that net force for this specific problem should be negative 384 newtons. We can see that we have a negative number, which means that we're slowing down, and that makes sense because our problem right here says slowing down. So if we want to solve for this acceleration, we know that net force is equal to ma. The net force is negative 384. The mass, well, it's the same person, so it's 80 kilograms times acceleration. Divide both sides by 80, and we find out that the acceleration should be equal to negative 4.8 meters per second squared. Now that we have our acceleration, we can find out what direction it's accelerating in. Since it's negative, that's going to mean that we're accelerating in the downward direction.